processes. We saw it before for seeing if something's alive. We saw it for monitoring. It also can maintain a phone book, a registry. So when a process spins up, it can actually say, hey, register my process ID, which it can get with self, by this name. Now, the process can do it as part of its own initialization. Whoever spawned the process and got that process ID back can do it as well. Somebody then just simply says, we'll refer to processes now by name instead of just some number. Okay? The name won't change, even though the process ID might change as that process crashes and comes back multiple times. So when we first start up, we say, hey, this process with this name is at this process ID. So we can register it, and of course, as things die off, intentionally just terminate, they've done their work, we can now unregister them as well. The key thing is now, anyone who wants to communicate with a particular process can use process.whereis to actually get the process ID for something. So I can actually say, where is the optics shop? And even if the optics shop burns down and comes back up with a different process ID, when I later ask where is, I'll get the new current ID. Right, so let's look at that in the, sorry, before we do that. Questions on this? So we're just going to maintain a named process ID dictionary, a registry. Yeah?
So how would you like dynamically register new stuff via code? Because like, how does the name work with uniqueness?
Ah, you're starting to see the problem. Remember I said this solves some of the problems, but not all? The big one it doesn't solve is scaling. This approach has problems scaling. So 100,000 processes, we got to make sure we give them all unique names. You're seeing already exactly one of the big weaknesses.
Even this is assuming the database doesn't crash.
Yes, so you have the global database of that. Now, one of the things that you can do, though, is we're going to start introducing the idea of processes that can watch other processes and bring them up accordingly. If this database that has everybody's process ID goes down, maybe the whole system has to be restarted. So this could be one of the critical processes with it. So we can register names and names and process IDs. We can unregister them, and then we can also ask what process ID a particular name has. Now we can also, remember I just mentioned linking or monitoring processes. There's two ways of doing this with the process module. You can link another process, and so what happens is if I link two processes, or process A links to process B, they're in it together, right? One dies, the other dies. So it's sort of saying, all right, we're in this together. We're both stay up, or we both stay down, or we both go down. And of course, a process can link to multiple ones. So you can actually have a set of processes where if one of them dies, all of them will automatically be sent, all the other ones will automatically be sent the exit signal. Can you think of why you might want to create a situation like that? Or why you might want to do that? Yeah.
Like you said, if you have a system critical process, it doesn't make sense to have the rest of the system still running depending on a process that's already crashed.
Exactly. And then you can also think of something that's maybe not critical to the entire system, but is critical to a small subsystem. And so you might have processes that are dependent on each other. Maybe I can only continue to do my job at least as long as I know this one is up and functioning correctly. And if it goes into a bad state and terminates, I need to recognize that or be told that. I'll exit and I'll come back up too. And so linking processes makes it so that, again, if one dies, the other is automatically sent the exit signal. So that's link. Monitor, though, is a little different. Monitor says, I'm gonna watch this process. If it dies, let me know. Don't kill me like Link. Just let me know that that process died. So what will happen is if I monitor a process, and we saw this with the medic example last time. If I monitor a process and that process goes down, I automatically get a message that lets me know that process went down. And then I can deal with that appropriately. I can say, oh, that one went down, I can restart it, like the medic example. Or that one went down, I better kill off this, and this one that I know depend on that, and restart the whole set. Or whatever, however you've architected the system. So you can link, which is sort of, if you'll, sort of a mutual pact, if you will. One goes down, the other will go down. And I can monitor. One goes down, it lets the other know. Or the system lets the other know. So let's look at this in this kind of a scenario now. So first off, the process ID passing. We're not going to simply pass raw process IDs anymore. We'll look up what a process ID, where a particular named process lives, using the process registry, and then we'll send that ID. So instead of saying send to some process ID that's for the analyst, I would say send to the process ID that I get by asking where is the analyst. So I'll say where is the analyst, it gives me back the current process ID for the analyst, and I'll send it, again, the picture. The analyst then sends what's the current, it asks where is the shop, the optics shop, and it sends the prescription. Now, remember I mentioned the example, the optics shop burned down, let everybody know it restarted. I don't have to let everybody know. When I detect that the optics shop has gone down and restarted, we'll talk about that in a minute, I can unregister the old process ID, register the new one, so that every time the analyst now asks, where is the shop, it's transparent. It might have just switched process IDs, but every time it's going to ask, where is it now, and send to the appropriate process. Yeah?
What about the time when the optics shop is down?
So there is a slight issue with potential race conditions that way. So you do have to be somewhat careful of that. But remember, the communication is send and pray anyway, so there's all kinds of other things that can prevent that message from going through. Again, though, if it's a critical message, you might architect that once it's received, an acknowledgement is sent back, but you have to set up the protocol for them doing that. That's actually done a little bit in the OTP part that we'll talk about coming up. But basically that I could also send and wait some period of time before timing out on receiving a message and then go ahead and retry or something like that. Notice also, I don't have to pass along the process ID for the customer anymore, because the optics shop will then simply say, where is the shipping department, and send the glasses there. The shipping department can then ask, where is the customer, and can send it there. Now this is kind of a simplistic example with one customer, you'd have to do it different, but building this system is not the point. The point is the communication and processes in it. One other change with this, so the big thing is we're now just relying on named processes here and always asking where is that process. We'll introduce a fifth process, an additional process into the mix. This is often called a watchman or a watcher or a monitoring process or all kinds of other terminology. We're going to introduce a process that's going to monitor each of these processes. Now, typically they're not going to be, you can sort of think of there's a wall here that's the interface for some client, and this is all sitting on the server. So the watchman's going to be watching these processes. And if one goes down, it will restart it and appropriately update the registry. So, registering process. Advantages. Big thing is it eliminates the need to be passing around process IDs. I don't have to get a process. You don't have to pass me process IDs. If I need a process ID of some named process, I'll just look it up using where is. It allows for a single process to monitor multiple things simultaneously using this monitor kind of command. The watchman can monitor multiple things and then restart them appropriately. Again, the big thing is we can reboot a process and don't have to do notification. Yeah.
So for our project, we're going around and processes are gonna be deleted. What happens if Watchman gets deleted? What's watching Watchman?
Well, yeah.
Okay, 'cause
That's
that
a
could-
great question. And
Alright.
you hit on one of the key things, which is who watches the watcher. And we're going to talk about actually constructing hierarchies, and we'll get to that in just a minute. All right, so again, you can reboot processes. The processes can come back up with a different process ID, and you don't have to notify anybody. They just get the new ID when they ask for the current address of it. Or as we put on the slide, no one will ever know that the optics shop burned down. They also don't need to know the chain of commands. So remember how the analyst was passing along its own process ID, but it was also passing on a customer one? And then maybe something else has to pass on another process ID from something much farther up the chain? That goes away. I don't have to. If I need to communicate with that process, I don't have to have all the other intervening processes pass the ID along. I can at any point just ask for its name. You hit on the big con here, the big drawback to this, is it doesn't scale well. You have to come up then with naming conventions for how you're going to name the processes. So if you're writing one piece of code and I'm writing code for some other process, the only way I know what your process is going to be named is through documentation. So we've got to document that, we've got to come up with naming conventions, and we've got to be able to scale that for large systems. And that just doesn't scale well. So, in terms of our goals, this can work for the first one, right? We can now bring processes down and bring them back up through both a process ID registry and then also this ability to link and monitor processes. Okay? But the naming part alone doesn't really scale well. So we haven't really solved the second part of the goal. So let's talk about the third part of the goal. And to do this, we're now actually going to start using OTP, this Open Telecom Platform. It actually bakes into the system a lot of these kinds of things. So process registry, name, it will actually maintain a separate process that is a server for monitoring names and so on. So again, because this is what the language is really built for, is large-scale concurrent processing. There's well-developed, well-tested, these things have been put through their paces a lot, libraries that you can use for building in these kinds of behaviors. And that's what they're called in OTP, is behaviors. You'll notice if you read the documentation, you may see behaviors with the British spelling, the IOUS. I served a mission, sorry, IOURS. In English, you don't have the U, right? I have to admit, I was looking at this for a while before it ever dawned on me that it was spelled that way, because I served a mission in England. This is just normal. But also, remember that a lot of this originated out of Ericsson and some other companies in Scandinavia. So it's kind of British spelling of it. So these kinds of libraries are known as behaviors, and they're built-in frameworks for different kinds of processes that you might have, and it already implements some of the behavior of that process. So the key thing is you don't have to do it if you're using it. You just say, oh, I'm going to create some process that implements this type of behavior. Actually, really, it's this module implements this kind of behavior. Think of it object-oriented programming. You're sort of inheriting all the good stuff that's already baked in the libraries for that behavior. It's part of, so all this hard work of knowing when to send and receive, sending acknowledgements back if you want to have like a synchronous, not just asynchronous communication. Remember, messages in Erlang and Elixir are asynchronous, but you can always build your own protocol to do synchronous communication. In other words, send, get an ACK back, and so on. On top, so you can build synchronous on asynchronous. but not necessarily the other way around. So it has stuff for doing that as well. It's all part of the Open Telecom platform. So if you're reading documentation for Elixir and Erlang and you see OTP, that's this set of libraries. Okay. Originally built for Erlang, but again, also available for Elixir. So let's look at some of these behaviors. We're only going to use two, but it actually supports multiple ones. One is a gen server, a general server. Sorry. So if I have a general server that's performing some functionality, then there are certain things I'm going to do. I can do initialization when I first come up. I can receive messages. I can register my own name with something. I can look up what names are, and so on. So gen server is just sort of a general server and a client server kind of a relationship. But remember, we also talked about this watcher or watchman behavior. The job, so if you go back here, each of these are sort of separate servers. This isn't really a server. No one's really trying to send communications to it to get to have it perform functions. Its job is to watch or supervise these other processes. So in an OTP kind of a framework, analyst, optics shop, and shipping department are gen servers. The watchman would be a supervisor. Now you might have noticed I left off the customer. Well, remember right here is sort of the interface to the system. So this is the client. These are sort of a set of servers handling the process. This is the watcher or supervisor for that server, set of processes. Okay. So we're going to use gen server and we'll use supervisor. Be aware there are others. One useful one is the finite state machine one. So as it receives messages, you can actually have it keep track of current state. So if you think about what you do with servers, often you'll send one message and then sort of remember I'm now in this state, and then I'll send when it gets another message, it will transition to another state based on the messages it gets. So why not just build that in? So a lot of servers, if you actually look at their operation, they basically are doing finite state machines. So we can build in that kind of stuff. And there's also one for just generic event handling as well. So these are all built-in libraries in Erlang or Elixir. So let's look at gen server. It sort of gives you a standard interface for building a client server setup, at least the server part of it, and then the interface that the client would use. It basically then, like all frameworks or libraries, the goal is to let you program on, or let you focus on what's the functionality that this server is supposed to do, as opposed to all of the other communications protocols and all the other stuff. Now, it has a number of functions that the client can call. These are the ones that we might be using. It has others as well. So these are things, again, remember, it provides an interface for clients to interact with that process. Remember we talked about building, I could build a module, part of which is code for running the process that's some server, maybe helper functions for it, some of which are modules for interacting with that. So if you think about the Christmas, the North Pole example, there was a write letter function. Okay? This is part of the interface provided to the client. Gen server tries to standardize the interface. So here are the things that, again, client code can call. This is not code that you'd call within a gen server unless you're talking to another gen server. This is something a client might use. So if I call genserver.startLink, that starts a gen server, and it also links to that current process. So this says, start up this server, and by the way, link me to it, so if it goes down, I'm going to go down. Okay. Call makes a synchronous call to the server and waits for its reply. So remember I said that all the communication is asynchronous. This one actually builds a layer of send and ACK back. So call, cast is an asynchronous message. This is like send, basically. I'm going to just broadcast this, and it's the send and pray. Stop, tell that server to stop. So somebody externally can tell the server to stop. And then I can also ask where is, and get I can invoke where is on that server and get its process ID to start communicating to it. Okay. So I don't even necessarily have to have the name of the server. If this is provided in the code for the module for the server, which is basically implementing the gen server behavior, I can just simply say, hey, what is your process ID? Okay. And it knows to ask by its own name. So these are an interface for interacting with a server. There's also functions that you can call from, the gen server itself has certain things it can call and use inside itself. But also it provides callbacks. Have you all seen callbacks in an event-driven GUI, perhaps kind of a context? You can also implement callbacks in lots of other libraries. So these are methods or functions that, these are functions in modules that implement the gen server behavior that the module has to implement. Okay? Because the system will interact with that module by invoking these particular functions. So you have to implement an init method. It might do nothing. Okay? Sorry, I'm using sort of methods and functions somewhat interchangeably. You implement an init method or function that will be called when a gen server process is started up. There will be a call to your init function, which now gives you an opportunity to actually start initializing yourself. This is very common in all kinds of sort of callback kind of frameworks. Also, there's a callback for handling a synchronous call or handling an asynchronous cast to you. So we'll implement these three callbacks. One lets you set up your own initial state. Another says, hey, somebody actually just used this gen server call function. And, sorry, they just used the gen server call function. You better handle this call now. Okay? Or some client used cast to send you an asynchronous message. The gen server behavior, it does the appropriate receive. You don't go into a receive state. It will handle the receive and then invoke your callback that says, oh, here, handle the cast. Does this make sense? So from event-driven, think of messages being like events in event-driven programming. When you write handlers for various things, or you write widgets and GUIs, you'll actually implement callbacks. Right? When the user does this, call this function on this. And this is what these are. All right, so let's look actually at an example. This is what the analyst module could look like. So let's define a module called analyst. We're going to use gen server. So that says, hey, I'm a gen server. This module is implementing the gen server behavior. So it inherits, if you will, all of the functionality of a gen server. Here are the three callbacks I'm going to implement then. Notice I don't implement this functionality provided to the server, to the client. That's all inherited, if you will, from gen server. I just have to implement these callbacks to actually implement the actual functionality of my server. So init, maybe we'll just simply put a message to some sort of log that says, all right, I'm ready to go. I'm going to the first thing I do is I'm going to register myself under this name. Okay. So now I've registered with this process registry. When I handle, when somebody broadcasts a message to me, I handle cast. I get a picture. I'm actually not going to, this additional parameter here, if you look at this as state, and take a look at the documentation for this, in terms of, it allows you to sort of pass additional state information. So if you send me a picture, I'm not going to care about what the state is. I will do an analysis of that picture, come up with a prescription, and then what I'm going to do is I'm going to invoke I'm now the analyst, which was functioning as a server to the client or to the customer, becomes the client for interacting with the shop, optics shop server. And so I'm going to ask where is the optics shop, get a process ID back. I'm going to cast to it the prescription and then my own process ID. Now, the callback for handling a call in our system, all these things are asynchronous. So for call, I can say, send back a tuple that says, I don't know how to handle that. Okay? Talk to me asynchronously. Now you'll notice that there are different sort of things I can do here. This is one where I create and return a tuple that says this is a reply. In other words, that will actually go back to the person who called this, who tried to send me a call. This is something where you're going to have to, I can't sort of just read off the entire documentation in class. You're going to have to take a look at the documentation for these things, for the assignment. Okay. I want to give you a feel for how you use them. Now, the way this would work then is we would start up, so I would basically say, I'm going to start up a GenServer, so GenServe start the analyst module. I'm going to get back a tuple that says okay, meaning it did start it, and here's the process ID. When I start it up, the system will automatically invoke the analyst's init function here, and that will write out, I'm ready to go. And then I can call to this process ID and send it the picture, and remember, it doesn't handle asynchronous calls. So I have to actually put in the module I have to put into the code, don't handle this particular call. Okay? But if I send a cast to it, which is the correct way in asynchronously sending a message, it says okay. It processed it, and notice I never actually sent back an okay response. If I don't send anything else back, it just says okay, that message was sent. So here's what our system looks like now. So our watchman can be a supervisor behavior. We'll talk about that probably next time. These three would all be using gen servers. The customer itself, this might be a gen server. Or maybe actually, instead of putting a wall here for sending messages, I put a wall here, an interface where people would call my code, and maybe a server that handles customer requests would start sending these things off. These could all be gen servers. This would be a supervisor. And now, instead of using send to directly send to a process ID or send to a looked up process ID, I'll just use gen server cast to send a message to a gen server. Okay. So all the same pros before about looking up things, about having supervisors. The protocols always stay consistent, which is nice because you're using these libraries. Here's the cons though. It doesn't handle the scaling problem yet, but it builds it into that framework are the keys for building scalable processes. And again, one other thing that we haven't talked about, having a single watchman for an entire 100,000 process system is not really that feasible. Especially if I want to start creating some new subsystem. I can't just handle things locally. I've got to register all that with the global watchman. Okay. So here's what we'll do, and we'll implement, we'll wrap up on this idea. So we've met this goal. We haven't yet achieved the scalability. I'm going to jump ahead. Here, we'll talk about this next time. I just want to introduce the thoughts now since the bell's about to ring. There are interdependencies between processes. Even though at a language level they're all independent, when you architect them, you'll have this cluster of processes working together and maybe form some subsystem. And this cluster of processes working together in some subsystem. And maybe this cluster of clusters is some larger subsystem that's part of the whole architecture. And so here's what we're going to do. We're going to have local name servers for each subsystem. So I don't necessarily have to have a global registry anymore. I can set up local registries for local clusters of dependent processes. Those clusters of dependent processes, instead of having one global watcher for everything, each set of dependent processes will have its own local name server and its own local supervisor that's responsible for starting them up and restarting any of them if they go down. And that's where we'll pick up next time. And that part that we'll talk about next time is what you'll actually be implementing for the next slide.